Hello TGS 300 and welcome back to the 7th laboratory session, Quantitative Methods for Spatial Science. Hopefully you've already seen the lecture that preceded this, and now we're going to be able to go over those 4 or 5 statistical tests that we've covered kind of mathematically within the previous session. And now I'm going to give you a bit of an overview for how we would actually kind of tap this out in a few lines of code, essentially to be able to produce those test statistics and evaluate different questions that we might be interested in based on the kind of drive that we've got in this particular week's lecture focus. Okay, so you should be able to download this code from the Blackboard website, and you should be able to open it up on your own machine. Obviously, it kind of describes those different tests that we've got here. First, we're going to start with this 2-sample difference of means test that we already covered. And I'm just going to produce the math for that particular example. So it's for this one here, so where we're comparing the means of 2 independent samples for difference. And we have an example here that we're going to apply this particular statistical technique to. So this is focusing on the data based poverty rates by state for the years 2000, 2010, and 2012. We need to load that data in first, okay? So essentially the states that we've got are categorized into different geographic regions across the United States. And it's hypothesized, this will be the focus of our first question, that in the West, so the west coast of the United States, the western part of the United States, where many of the cities have a booming tech industry, there is essentially, as a consequence of that, actually lower poverty rates than compared to other parts of the US, for example, the South, where maybe you have a less developed economy. I don't want to say developed, but less booming economy, and maybe there are more kind of structural employment issues within some of those more southern states. That are present there. Okay, so look, let's get into the data anyway. So you've got this code which we've opened up before. So basically here I'm going into the RStudio application programming interface and obtaining the path for the current code that I've got, and then I'm setting that as the work directory, and then within that work directory, so this set WD is set the work directory for the folder that we've obtained, which here on my computer is under this path. And then essentially we can use read.table in order to load in this poverty database that we've got here. So this is each of the 2-letter state codes for all of our entries. So we've got 51 states, obviously, just here, each one row for each state. We've got the region, whether it's south, west, northeast, or midwest. And then we've got the year, okay, so this is 2000, 2010, 2012. So the reason why this has an X before is that R doesn't really like you or won't allow you to have column headers which have numbers starting that particular column name, okay? So here you couldn't put 2000 or 2010 or 2012. You have to put the X in front in order for it to allow you to actually use that as a column name, okay? Now what we're going to do is we're going to create a vector just from those entries, in this case, which are in the western region. So what this is saying is for my data frame poverty, access the 2012 column. And what we're going to do is we're going to say subset those regions which equal W, so the western regions. Okay, so this just produces a vector of values specifically for the western part of the United States for those poverty rates, okay, so from 10, 19, 15, 11, etc. up to 9.6. And we can do the same here for the southern poverty rates, and then actually now we've got both of these poverty vectors in our global environment, we're able to take a statistical summary of them, okay, so we can do that for the west and the south, and this summary function provides us with the minimum, the first quartile, the median, the mean, the third quartile, and the maximum values within that data set, okay? So for poverty in the western United States area, you go from a minimum of about 9.6% of the population living in poverty up to about 20.4% of the population living in poverty with a mean of 13.86. Whereas for the southern states, you have 9.9 as the minimum value, 22% as the maximum value, and a mean of 16.9. So already we can kind of see from these underlying statistical summaries that the South probably does have, or it's indicating that it may have higher poverty rates than the West. But what we haven't been able to do yet is to actually statistically demonstrate that to a certain confidence level. So it could just be that these results have just occurred by chance, and therefore we need to actually statistically test the likelihood of these events occurring by chance. So we can look at the poverty rate. So here's the Western poverty rate. So we have 3 states as the maximum for any of these here, and they're between 10 and 16% in kind of the middle of the distribution. And then for the southern states, we've only got 1 state for each of these lower buckets here. And then for 16 to 18, we have 7 states. And then for 18 to 22, we have 3 states, okay? So look, now we're going to focus on carrying out the t-tests that we want. So we know that we're interested in whether the West has a lower poverty rate than the southern region. So that's going to inform our alternative hypothesis. So the X bar, the mean value for poverty in the West, we expect it to be lower than the mean value for poverty in the South, okay? And then for the null hypothesis, obviously this is just the status quo. It's just where we don't think there is any kind of significant difference between the West and the South. So we assume that the mean poverty rate for both of these geographic areas would just be the same, okay? So we could say that they're equal, or we could subtract one from the other and assume that they equal 0, okay? So now we've defined our hypotheses, we need to define the test. So we have 13 states in the Western sample, we have 17 states in the Southern sample, and then we have an X bar for the first sample of 13.86%, and we have an X bar for the second sample in the South of 16.9% as the average poverty rate. And we then have a standard deviation of 3.27 for the West and 3.22 for the South. Obviously, both of these samples, they're not over 30, and therefore we'll be using the t-distribution rather than the Gaussian normal distribution, so the z distribution, I should say. And basically, we need to choose our significance level. So, as you'll remember from a lot of our other tests, we want to be at least 95% certain that the result hasn't just occurred by chance, okay? And that's kind of a fairly standardized confidence level that we want to have within our statistical results. So our alpha value, if we want to be 95% certain, will end up being 5%. That's our zone of significance within the distribution. So if we get a value within there, then we would reject the null hypothesis and accept the alternative hypothesis at that 95% confidence level. We need to get the number of degrees of freedom, so that means that we do need to add together the 2 samples and then subtract 1 value for each of them, so we would end up with a number of degrees of freedom, a number of degrees of freedom that would equal 28. So we've got 30 samples overall, we subtract 2 and that gives us 28 degrees of freedom. And then we need to delineate the region of rejection, okay, so remember that it isn't explicitly necessary here. We could just use a p-value, but because we're trying to skip some of those steps within the kind of classical hypothesis testing approach, it's worth us just reminding ourselves that we could get this t-critical value by basically using the quantile t-distribution function here, giving it the alpha value, the number of degrees of freedom, and specifying which part of the distribution we want to actually have the number of standard deviations produced for. And then basically when we plot this within the distribution, we get that t-critical value level, which is minus 1.7 standard deviations, plotted out down here as our zone of rejection or acceptance. Okay, so it's the critical value level within our distribution. So obviously, if the value that we obtain is within this red region, then we would reject the null hypothesis, accept the alternative hypothesis, and basically we would be able to conclude at the 95% confidence level that the poverty rate is lower in the western part of the United States compared to the south. We then need to calculate the test statistic. So you remember that within this approach, we need to get the difference between the samples and the standard error of the difference between the means. So this is fairly straightforward. So let's get this standard error down here, which means we take the square root of the square of the standard deviation for the first sample divided by the number of samples and add it to the square of the the squared standard deviation for the second sample divided by the number of samples, the entities that there are in the sample. Okay, and when you do that, you end up with this particular equation here using the separate variance estimate. So this SE value that we obtain here is 1.196. And we can then get this t value really easily, okay, because we've got the SE, this standard error bit here, and then we just need to subtract the x bar 2 from the x bar 1, okay, just to complete this part of the equation just here. And that gives us a t value of minus 2.5, okay, so that's really quite significantly lower than our t critical value, which was minus 1.7, so it's very much in this zone of red down here, and therefore we can say at the 95% level that we are going to, we have enough evidence to reject the null hypothesis and accept the alternative hypothesis because we believe, based on the evidence that we've got, that the poverty rates are lower in the western part of the United States compared to the south. Okay, so that's how we do it. We do it using the kind of classical hypothesis approach. We can also get the p-value by basically using the probability, the PT function here. So this is basically saying, give me the probability for this value within the t distribution. This is the number of degrees of freedom that we have, and the p-value that we obtain is minus 0.008. Okay, so it's really small, much below 0.05, and therefore we know that the result that we've got is significant at that 95% level. We can also just use the inbuilt t-test here. We can give it two different data sets and plug in the numbers that we want to use, and it will basically reproduce that two-sample t-test value. So we're getting the same p-value here and a very similar t-value to what we calculated by hand in the previous examples. So what happens when you've got non-parametric data? Well, obviously we can use that Wilcoxon rank sum test, but we're going to need to basically rank this data. So first we're going to need to basically put all those values in a single location, a single data structure, so that we can tell them apart. We'll need to basically make an indicator as to which one that they're part of. Okay, so what I'm going to do here is, when we repeat this here, this is saying let's repeat west here. The number of times equals to the number of samples. We're going to concatenate these results into a single vector. So when we get class, this is just literally the number of times that we've told each one of these to be replicated for west and south. And then we can take the proportion here for those two different values. So these are the proportions of the poverty rates, and then basically we can combine them using that data.frame function that we've used previously, and it just places them all within a data frame called values. Okay, so if what I did was confusing to you there, you can break it down as the first line basically produces this class vector, and it just repeats those west and south statements, the number of sample times that are required, and then the second we just basically produce the proportions. And then finally, we stick them together into a data frame, okay, so that we're able to access them. And then essentially, we're able to actually rank these, so we can produce the rankings. Sorry, apologies, I just had to pause the video very quickly because my dog was barking at the door. So essentially what we've done is we've produced these data frame this data frame of values for the classes and the proportions that we're interested in, and then basically we're able to rank those. Okay, so if we produce the ranks, this is basically saying at what point each one of those proportions is relative to all others once you've actually ranked them in order. We can create a combined data frame this way by using the cbind, so that's just binding the columns basically. So rbind is binding rows, and cbind is binding the columns, so you can look at those functions. But easily, if I just, it's kind of more easy for you to understand what I did if I just look at this combined data frame here, because you can see that what we had before was just the class and the proportions. And then basically what I did was I added that ranks vector to the side of it. So obviously if I click rank here and I rank based on the rank value, we're going to have rank 1 allocated to the smallest proportion, rank 2 to the next, so on and so forth. So if we go all the way down to the bottom, we're going to have the largest proportion here. Okay, so the state with 22% of people living in poverty, well then that's going to be rank 30 relative to all the others, okay? So hopefully that's kind of clear to you now what we mean by rank, because I know in the actual lecture I was talking about ranking this data and what did that actually mean, and obviously we're basically putting our data rows in order and then giving them a value of 1, 2, 3, 4, going from the smallest up to the largest. Then we're able to produce these vectors here by basically saying go into my combined data frame, and then for the combined data frame for anything that is equal to the class West, get me all of the rows. So this is subsetting into the data frame, combined data frame, and then the comma here is saying give me the rows. So we can basically allocate that into our memory, and that's giving me just the West rows here, okay? We can do the same for the South, and this is giving me just those rows which are equal to the South, okay? And we've got all the proportions of the ranks for them here. So let me go to the math so that you can remember exactly what we're trying to do. Right, so this is where we are within the actual lecture. We need to get this ZW value, and we need to calculate this for one of the samples. Okay, so here it just says WI, but you could do this for the first one and the second one. It just depends. The one that you choose, it will end up relating to whether it's a positive or a negative sign. Okay, and we need to get this W bar, which is the mean ranks within that sample, and subtract it from the WI, which is the sum of the ranks, and then we need to divide it by the standard deviation of the W value. So when we basically do that, we can get the W1 and the W2 values for each of the samples just by using the sum function on the ranks, and that produces these W1 W2 values here. So we've got 145.5 for the sum of the ranks for the first sample, and 319.5 for the sum of the ranks for the second sample. W is the sum of the ranks of the class, okay, so this is just repeating what I said before, which is that you can basically carry this calculation out on the first sample or the second sample. It doesn't matter which, it's just going to depend on the kind of sign that you're going to get for the final test statistic. So we can get this W1 bar value, which is this one here, which we're going to need to calculate in this way. So Ni times by, and then we need to get the outcome of this, equation here. So basically, I've reproduced that here for you. So N1 times, and then we have the numerator, which is N1 plus N2 plus 1 divided, and then we have the denominator divided by 2. And this gives us a value of 201.5 for that W1 bar. And then we can do the same for the SW value, which is the standard deviation of W, which gives us 23.89. And then we can basically stitch all of those values together that we've got to do that kind of simpler equation here to get this ZW. So we can subtract the W1 bar from W1 for the numerator and then divide it by SW. When we do that, we end up with minus 2.34 standard deviations below the mean for the test statistic here. And then if we actually allocate that ZW test statistic that we've got to, we can use the normal distribution here, we can look at the probability of this occurring, because we've got more than, we can allocate this to the p-norm function here and specify where in the data set we're interested, and it will give us the p-value for that test statistic that we just obtained, okay? So essentially what we're getting here is 0.0095, so this is far, far below that 0.05 threshold that we would normally look at to be 95% certain that the results haven't just occurred completely at random, okay, completely by chance. And so as a result of this being so small, this p-value, we're able to basically reject the null hypothesis because we've got quite substantial evidence that the results haven't just occurred by chance, and accept the alternative hypothesis that the poverty rate is obviously lower within the South relative to the Western parts of the United States. We can also use the built-in function to check this. So we get a slightly different p-value, but pretty much similar case, a slight amount of rounding. So basically what's happened is that there might be a minor difference in how it calculates the ranks, okay? But essentially this is producing pretty much the same results as what we calculated above manually. Okay, so that's kind of 50% of the way through the laboratory session today. I hope I haven't lost you. If you need a break, don't hesitate to just click pause. Take a minute to have a breather, get a cup of coffee or a cup of tea, go for a 5–10 minute walk, kind of clear your mind, and then let's start again on the next set of equations. So now we're going to focus on matched pairs difference tests. So you remember before we were focusing on independent samples where basically you could have values for house prices in either Fairfax City or Richmond, for example. And essentially they would be completely independent, those samples. But matched pairs difference tests are where we might have one sample of people or of houses, and then, for example, what we might do is we might repeat that sampling process at a later date in time, okay, a later point in time. So let's say we want to look at house prices in Fairfax in 2019 and 2021 and we want to compare them, and we're going to end up using basically the same sample data points just at two different points in time, and this matters because there's not an independence between, there's no independence between those samples, okay? The results are dependent on you sampling the same entities twice. So in the same data set, we've got data for poverty by state, but this time we've got the time series between 2000 and 2010, okay? So in the year 2000, the American economy was very hot. It was just before the dot-com boom. The dot-com boom and bust, I should say. It's in the middle of the dot-com boom, so this is when the internet and websites were really first kind of kicking off. And essentially the poverty rates at that time, we suspect, were probably lower than they were in 2010, and that's because the global financial crisis in 2007, 2008 really did take a bit of a, it really did give the US economy a bit of a kicking because of the amount of dependence that many people had on financial credit, and kind of how the housing market was very much linked into the growth of the economy, and eventually that all collapsed, unfortunately, because of people over-lending to people who weren't able to afford the debts which they had. So this is very, very bad financially. It was very bad for people who were affected, and therefore we suspect that the poverty rate would therefore be higher in 2010 relative to 2000, okay? So the key issue is, well, can we actually test if this hypothesis is actually true? Is there actually an increase between these two different dates? So the way we're going to do this is we're going to go into our poverty data set and refer to the X2000 column. So remember, the $sign refers to just accessing one column within that data set. We're going to allocate it to the poverty 00 entity here that I'm putting into the global environment. And then we can do the same for the data in 2010 as well. And then we've got those two poverty vectors here for 2000, 2010. We can then look at the summary of each of these variables, okay? So in 2000, the minimum poverty rate was 4.5%, whereas for a state across the United States, this is all states, whereas in 2010, the minimum poverty rate was 6.5%. And the maximum in 2000 was 17.5, and the maximum in 2010 was 22.5. So it indicates that there is an increase in the poverty rate, unfortunately. But what we want to be able to do is to test and actually test for the likelihood of this actually being a significant effect that we're measuring, or whether this is just basically purely occurring at random. So we can look at the histogram for these poverty rates in the year naught, so the year 2000, and we can see from 4% up to 18% is the shape of the histogram, whereas in the year 2010 we've got a shifting of the poverty rates, okay? So the poverty rates in general have shifted much higher, even to above 20 here. So you can see the difference in this distribution is much more more platykurtic, whereas by the time we get to this kind of 2010 distribution, we're ending up with kind of the distribution having kind of moved sideways, also shifted upwards, and there being many more states in the middle of this distribution as well. Okay. So look, now we've got that data, we're actually able to carry out the t-test by hand, for example. So let's state our hypotheses first. So the null hypothesis is that the difference between 2000 and 2010 is basically nothing. Okay, so we think they're essentially the same. Whereas the alternative hypothesis is that the poverty rate in 2010 is going to be higher than 2000. So that means that this is going to be a one-tailed test. We're only going to focus on looking in the upper part of the distribution. Relative to maybe if you don't know which way the effect runs, and you might have to look in both the top and the bottom part of the distribution. We need to define the test we're going to use. So we know we're using matched pairs here because we've got a dependent sample. And then we're going to use a t-test. Okay, so we need to get certain data metrics ready before we begin. So let me just find the math for this here. Okay, so for the matched pairs t-test, we want to find this TMP test statistic, which means we need this delta bar here, and then we need to get the standard error of the mean also as the denominator. So we're going to take the length of these vectors for the sample size for the first sample and the second sample, and we're going to take the mean for both of those samples for the x bar 1 and the x bar 2 values. And then we'll get the d value basically by subtracting the poverty rates between 2000 and 2010, okay? And that gets us our d values here, the difference from the matched pairs. And then basically we can start to do some of this number crunching later, okay? So we want to be 95% certain that our result hasn't just occurred by chance, so we're going to use an alpha value of 0.05, so we're looking for a significant result for that p-value to be below that 0.05 level. And to get the number of degrees of freedom, we need the number of samples that we've got minus 1, okay? And there's just one sample here, so we just use the normal sample size minus 1. We then need to delineate the region of rejection. So for the critical alpha value here of 0.05, the t critical value is going to be 1.76 standard deviations above the mean. And then when we enter all of that into our distribution, we're going to be looking at this zone of rejection up here, which I've highlighted in red. So if our test statistic lands in this red area, we will know that we'll have enough evidence at a 95% confidence level to reject the null hypothesis and accept the alternative hypothesis. So then we need to get our d bar, okay, so that's this, value here. This is the mean of the matched pairs, and we know that we've got our DI values and we've got the number of samples. So we just need to oh, that's right, we need to subtract these from each other. Sorry, I was just checking why that didn't quite match up with the equation that I was using. So I think there's multiple different ways that you're able to calculate this essentially. So basically here we're subtracting the mean for the second sample from the mean from the first sample, and then we're going to get the standard error here by taking the square root of the sum of the squared differences and then dividing by the number of degrees of freedom, okay? Essentially when we do that, we get this SE value here of 0.3, and then we can basically take the D bar value, which is our numerator, which is 3.39, divide by that, that SE value, which is 0.3, and we end up with a t statistic of 11.01. Okay, so this is really a large t statistic, and the point being that this is well beyond the number of standard deviations that we were looking for in order to kind of delineate our zone of rejection. So I think our t critical value was 1.67, and therefore if we've got a value of 11, this is going to be way, way, way beyond where we were expecting this to be. So it's really far out here off the side of the plot. So it's very, very convincing evidence at the 95% level that we should reject the null hypothesis and accept the alternative hypothesis. So what we're able to do is we're able to test that p-value. So we're able to give it the t-value that we got, and we get a p-value of 2.81 to the minus 15. So it's highly, highly significant. We're also able to test using the inbuilt t-test function for this paired t-test, and we get a t-value again of 11.015, which is very similar to what we obtained before, and then we get this tiny p-value of 2.815 to the minus 15. So now let's move on to the final, one of the final tests that I'm going to present to you. I think that, so what we're going to do here is we're going to use the same variables that we used in the last test, but basically do the built-in version of the Wilcoxon matched pairs signed ranks test. Okay, so this is the non-parametric version. And essentially what you're able to do is you're able to give it the poverty rate for 2010 and for 2000, and you're able to explain that it's a paired t-test and give it your confidence level, and you're indicating the type of the alternative hypothesis here. If you're not sure about how you enter this, look at the help menu for wilcox.test, and basically this is going to produce a p-value for your particular assessment, and here this is basically for a non-parametric approach, providing you with a p-value that's also highly significant. Okay, so if you were to go through the math for how you calculate that Wilcox test, which I showed you within the lecture, you would end up manually producing something very similar to this, but we're not going to go over that in a lot of detail right now, okay, because it's quite similar to the previous tests that we've carried out. So finally, I just want to finish by basically showing you how we do a two-sample difference of proportions tests. So before, we've been focusing mainly on continuous data, which is absolute. Whereas here, what we're going to do is we're going to look at the actual proportion of the data with some sort of particular outcome, okay, and compare them between two samples. So the two-sample difference of proportions test lets us compare those independent random sample proportions for their differences. And you can look at page 165 and 168 in the book, McGrew et al., in order to look at how this is carried out in more detail. Note that while this example seems to look like a matched pairs sample with looking at the year X and Y, these are independent samples because the same individuals are not sampled in both times. Okay. So we're looking at the obesity levels within Alabama in 2000 and also 2010. So unfortunately, the adult population within the United States, particularly in some of the more deprived states, has basically ballooned in terms of excessive weight over this period, and therefore we're interested in basically statistically testing whether the obesity rate has actually increased as we suspect it might have. So the obesity level for adults in Alabama has basically increased from 23.9% in 2000 to 32.8% in 2010, and therefore the observed difference in the proportions of equals is basically about 8%. Okay. So essentially what we're going to do is we're going to enter that data into the memory that we have within R. So for the sample size for 2000, we've got 2,156 people sampled, and in 2000 we've got 516 people sampled. So when we get the proportion there, so this SP2000 is going to be that 23.9% value that we've got. We can then repeat this for the number of people sampled in 2010, and basically the number of people ranked, rated basically as obese, and then it's going to produce a value of about 32.85%. Okay, so these are the two proportions that we want to test. Now we want to be 95% confident within our results, so our alpha value is going to be 0.05, and essentially we're then able to set up the data for this proportion test using a vector for both the x values and a vector for the n values. Okay, so I can put those values into the x vector and the n vector here, and then we can basically provide them to this prop test, so proportion test. And here what we're doing is we're giving it each of the vectors we just produced for the number of, so the values, the proportional values, the number of data samples that we have in each of those samples. We're specifying exactly what we mean here in terms of the alternative hypothesis. Obviously, we think that the proportion of the population has got more obese, and therefore we're thinking that the effect is going to be larger between the two samples, and therefore it's a one-tailed directional test. And then we're going to enter the confidence level, which is 95%, or here 1 minus the alpha. And then basically when we actually run through that results, what we end up with is the chi-squared statistic here, which is 62.043. So this test statistic in this case is listed as the chi-squared. As with the one sample version, we are able to also take the square root of the chi-squared value to give us the approximate value of what the z would be, which is about 7.87 standard deviations above the mean. Okay, so we can see from the built-in test that our p-value is essentially, let me find it, 0.07 here. Oh, sorry, my bad. Our p-value is here, which is 1.68 to the minus 15, so it's well below that 0.05 level that we're looking at for significance. And therefore this tells us that at the 95% level we can be confident the result hasn't just occurred by chance, and that basically we can reject the null hypothesis and then actually accept the alternative hypothesis, which is that the proportion of obese people within Alabama has essentially increased between these two time points. Okay. So look, I'm just going to close off the lecture now. I think you've got all of the ingredients that you need to be able to complete the assignment. Thanks for tuning in again this week. Sorry if this has been, quite technical and hard, but ultimately these statistical tests are really worth learning, and they'll really set you in set you on a good trajectory for your future employment opportunities if you can kind of start to master some of these statistical tests within R. Okay, so please do stick at it and let me know if you've got any further questions. So thank you very much for tuning in. It was really nice to see you. Have a very good day. Take care. Bye-bye.